Uh, Ladies and gentlemen, I think we can get started. We have about 16 participants. I will briefly introduce Oscar Sigwell Dawson, our guest speaker for today, and then he will give the PowerPoint presentation, and then the floor will be open for Q&As. So, ladies and gentlemen, my name is Armagan Al-Haq. I am the Manager of Program Development, Partnerships and Finance with the Waterloo Institute for Sustainable Energy here at University of Waterloo. And it's an honor for me to introduce our guest speaker for today, Dr. Oscar Sigwell Dawson. He worked with Acres International, a global consulting, engineering, and management services company for 38 years, including 9 years as president. His career included managing preparation of national investment and strategic development plans for energy and electricity supply with funding from international agencies. He is a director, former chair of the Energy Council of Canada, and a former member of a World Energy Council Committee on Global Energy Scenarios to 2060. He has served as director or trustee for approximately 25 publicly traded companies, private corporations, regulatory agencies, university, and advocacy organizations. He completed his undergraduate and postgraduate studies in civil engineering at University of Manitoba and at Imperial College, University of London, respectively, followed by postdoc studies in economics, environmental science, and systems methodology at Harvard University. He is a fellow of the Canadian Academy of Engineering, Canadian Society of Civil Engineers, and International Water Resources Association. He is a life member of the Energy Council of Canada. He has been listed in Canada's Who's Who continuously since 1993. Ladies and gentlemen, we welcome Oscar Sigwell Dawson. Oscar, the stage is all yours. Please go ahead.
Well, thank you very much, and thank you especially for the opportunity of giving this presentation. I'm very privileged to give a presentation to your institute, and I've gone through some of the publications, and it's a very impressive institute. So this is a great honor for me. So my presentation is going to be generally in three parts. The first part is I will provide kind of a global backdrop as to where we are with regard to progress on climate change and in particular mitigation of greenhouse gases. Then I will describe a special project which was carried out in the 2013 to 2016 period, which is referred to as the Trottier Energy Future Project. So I'll describe that and some of the key observations from that. And then finally, I'll provide some kind of summary remarks with regard to where Canada is on climate change and what needs to change and happen for us to perform better over the next 30 years. So just in terms of the history, it's useful just to have a very quick backdrop here. The critical highlights really begin with the Brundtland report in 1987. There have been basically 4 key summits. The first one was the Earth Rio Summit, which agreed that climate change had to be a serious consideration, and it set up the United Nations Framework Convention on Climate Change, which has been the basis for reporting for each of the various countries as to performance in terms of progress on climate change. You're all familiar with the Kyoto Accord, which was signed in 1997, and then I wanted just to mention the very historic Gleneagles Summit in 2005, which was chaired by Tony Blair of the UK. And that's a very significant development because it basically ended in a communique that confirmed that climate change is real, that the industrialized world needs to take a leadership on that. And then that led to a series of actions, very quick actions in the UK, beginning with a Stern Review on the Economics of Climate Change, which was published in 2006 and led to the UK Climate Change Act in 2008. This is a very significant act because it laid the foundation for basically assigning responsibilities for administering strategies for reducing GHG emissions in the UK and for formal reporting to Parliament every year, and also establishing very clear 5-year targets. So I'll come back to that a little bit later in the report as well. The Copenhagen COP meeting in Copenhagen 2009, and Canada at that time agreed to a 17% reduction by 2020. So I'll comment on that later. And then Canada formally withdrew from the Kyoto Accord in 2012. First country to actually withdraw formally from the Accord. So as all of this was happening, the Trottier, Laurent Trottier, who is an engineer, McGill graduate, and set up a company. He had a very prosperous company, so he set up his own family foundation, and then made a commitment in 2010 to fund a study which is the Trottier Energy Future Project. So there are basically two key studies that have been carried out in Canada. There was a study which was called the United Nations Decarbonization Pathways Project, which was completed in 2014. And that was a study of the 16 most highly polluting or GHG emitting countries in the world, which included Canada, the United States, and Mexico. And that was a study that was carried out that had results that were generally similar to what came out of the Trottier Energy Future Project, which was completed in 2016. Then, of course, we know that the COP21 meeting in Paris, where Canada committed to a 30% reduction, and then a further meeting in Marrakesh, where Canada committed to 70 to 90% reduction by 2050, and then the most recent in last year, when Canada then committed to being net zero by 2050. So that's kind of the historical backdrop. So this then brings us to the Trottier Energy Future Project. This was sponsored by the Trottier Family Foundation, commitment made in 2010, which was just after the passage of the Climate Change Act in the UK, and just before it was evident that Canada would come nowhere close to meeting its committed targets as defined in the Kyoto Accord. So Laurent Trottier was the leader, was his family foundation. He recognized that he didn't know, even though he said that we need to deal with climate change, he was not a specialist in this area. So he brought in two sponsors, which include the Canadian Academy of Engineering and the David Suzuki Foundation. These are both national organizations, but with very different cultures. The Academy of Engineering, of course, looks at things in a very fact-based, rigorous way, and the David Suzuki Foundation is more abstract and so on. So the whole concept was that if you could get agreement between two organizations with such different cultures, that this would be a great contribution. So the study was carried out over the 2013 to 2016 period, and a final report was presented at the Trottier Energy Institute in April 2016. And the report, which includes an executive summary, a project summary, and the detailed results of the report, are available on 3 websites as noted. So the goal as defined was to assess options and pathways for reducing Canada's greenhouse gas emissions by 80% by 2050 relative to 1990. This was exactly the same goal as in the UK Climate Change Act. So I was invited in 2013 to take over the project. It had been going, but it hadn't been going well. And so I was asked to do 3 things. One was to define an approach and methodology for how to develop strategies for achieving the stated goal. The second was to pull together a team, and the third was to manage the project. So what I did was I proposed an approach that was really built around systems methodology, using 2 mathematical using, two mathematical models. And so the key things is to have a very, very highly talented team and to have the rigorous underpinning. So we use both an optimization model and a simulation model. Both these models were models of the entire Canadian economy and represented all the provinces and territories and all the sectors of the Canadian economy. However, at that time, even though the models existed, they had never actually been applied in this way. So this was quite a bold decision, let's say. I would also note that the optimization model is a model that was originally developed for the actually for the U.S. Department of Energy, but then was adopted by the International Energy Agency. And the initial development was actually in the late 1970s at the time of the global energy crisis. So that has become the global norm for optimizing strategies for the energy sector, and now has been expanded to include climate change considerations. Now, given that this is the first time that a formal systems methodology approach has been applied using both simulation and optimization models, the big question was to make sure that the approach was credible. And so we needed to make sure that the data going into the models, was thoroughly studied and was peer reviewed. So we had 14 working papers, each dealing with different sectors of the Canadian economy. Just note that we come to this later, but the emissions include both combustion emissions and non-combustion emissions. And the options for non-combustion emissions were very poorly defined. So we focused most of our analyses on combustion emissions, but also did take into account in a qualitative way the impact from non-combustion emissions. There's a lot of work required in model upgrading and calibration. We had 11 scenarios. We organized the next 4-person expert review panel, which was led by Professor Andre Plourde at Carleton University, who chaired the 4-person panel. And then in addition to that, we had external reviews. So this study was very extensively reviewed. So basic premises. First of all, we had to define an objective function for the optimization model. And the objective function basically was to minimize the present worth cost of the future stream of investment and operating costs over the period from 2010 to 2050, 40-year period. But all of the solutions had to meet two goals. One was that we had a growing economy with increasing demands in the various sectors. So those increasing demands had to be satisfied. And secondly, we had mitigation constraints, which were increasingly stringent from 2010 to 2050. We did actually modeled population growth in Canada and showed that the population growth would increase from 35 million to 48 million by 2050. We also looked at GDP per capita and total GDP growth, with GDP per capita increasing from $45,000 a year per capita to $65,000 by 2050. And this is all in constant dollars. We use 2011 dollars. So the total GDP growth was slightly more than double over the 40-year period, again, after excluding the effects of inflation. We looked at every industrial sector of the Canadian economy and broke this down by projections of industrial gross output for each subsector in each jurisdiction. And then we also had to incorporate fossil fuel projections, which included both use in Canada and for export. main thing was to look at basic assumptions as to how much fossil fuels would be exported. So we had two broad definitions of fossil fuel projections. One was, which was really built around the report by the National Energy Board, and then we had a second one which was lower projections to reflect the fact that the world would likely be consuming less fossil fuels in future than at the present time. There were special considerations in the modeling. One was that when we were dealing with intermittent renewables have limitations which are really related to dispatch. So there is a limit on the amount of intermittent renewables you can put into an electricity supply system. We had to deal with the issue of dependable capacity. This again came back to intermittent renewables that have essentially no dependable capacity contribution to the electricity supply system. So the dependable capacity, this is the guaranteed generated capacity at peak system demand. So that had to come from options like hydrothermal, nuclear, and possibly others. When we had a lot of intermittent renewables in the system, the cost of grid supply increased also, so we took that into account. There was a lot of work done on biomass feedstock, and as we were looking at shifting some of the end uses from fossil fuels to biofuels, we then had to address the question of whether or not there was enough biomass available in Canada to meet the biofuel requirements. And in fact, there was a constraint. We had to look at cost variations over time, especially with things like solar, which have been coming down dramatically. Since this was the first time that this kind of a comprehensive systems approach had been used, we felt it was important to start with no development constraints, no equity constraints. So what that really meant was that we wanted the models to search for solutions that had as much flexibility as possible. So, for example, we allowed interjurisdictional connections, high voltage interconnections between jurisdictions. We did not include any political constraints, no regulatory constraints, no social constraints. We just wanted to see what does a minimum cost solution look like in the absence of constraints, but of course limited, but still having to satisfy the constraint limitations. So this is a very quick overview of GE emissions in Canada. This is 1990. And the key thing here is that we have non-combustion emissions, which is shown on the right, which represents about 28% of total emissions. These are emissions that are associated with industrial processes where CO2 is not used as a fuel, but they be used as a chemical, also methane and nitrous oxide and so on. There were also agricultural emissions, which are dominantly non-combustion based, waste, which was about 3% of the total emissions, and heat emissions. Now, with regard to the combustion emissions, which is the rest that's on the left-hand side, we had the combustion emissions for end users, which was transport, industrial, residential, commercial, and agriculture, which represented almost 50% of total emissions. And then the other emissions, electricity and fossil fuel production, were really what we call the supply emissions. This was the emissions associated with extracting oil and gas, for example, transporting it, refining, distribution systems, and so on, to the point of end use. So, roughly speaking, the end uses were about 50% of the total emissions. The supply was about 25%, and the non-combustion emissions were just over 25%. We had 11 scenarios, and I won't go through these in detail, but just to give you the overview. So we had generally going from, we always had to have a reference scenario, so that no reductions in GHG emissions, which was really based on just the assumption that climate change was not a consideration, so it was business as usual. And then we had a series of scenarios which were built around both always having GHG emission constraints, but then having a series of additional considerations, such as we had no additional high voltage interconnections, and then we had allowed high voltage interconnections and models to select the capacity of high voltage interconnections that satisfy the minimum cost objective function. We had changes in urban form. We had second generation biofuels. We included carbon capture and storage later in the study, because at that time it was not really a proven technology, so we refer to that as a disruptive technology. Today it would be regarded as a proven technology. We looked at increasing export to the United States. We looked at what the solution would look like if there were no more nuclear in Canada, and then biojet fuels and so on. So quite a broad range of scenarios. Canada was represented by its 13 jurisdictions, the 10 provinces and 3 territories. So these are basically individual units in both the simulation and optimization models. The energy system was represented for each jurisdiction, really going from the resource side, which is on the left-hand side, to the end uses on the right-hand side. So not to get into detail here, but this is really the flow from extracting your basic primary energy resources and then simulating all of the various conversion processes that go from there towards eventually meeting energy demand for services. So the model results were really driven by defining the demand for energy services, which is the right-hand side of this diagram. And then we have all of the relations going back to the primary sources and including all of the costs for transformation and distribution and transportation and so on. So this was a very comprehensive representation. And even when we looked at the demand for energy services, we broke those down into a very large number of subcomponents, including, for example, in transportation, we had heavy-duty transportation, which then was broken down between rail transportation, heavy truck transport, and so on. On the light-duty vehicles, we broke it down between urban transportation, we had cars and light-duty vehicles, and then we had heavy-duty vehicles and so on. So it was a very detailed representation of end uses. So with the two models, there was a tremendous amount of data flow between the two models. I won't get into this, but it's just to demonstrate that in fact the data flow worked both ways. We had, with the authorization model, you have a higher level of aggregation. So we provide results to the simulation model and simulate certain parts of the system in much more detail. We also use results in the simulation model to provide definitions for the authorization model. So this data bridge was a very important part of the overall process. So now just coming quickly to results. This was a result which showed that if you do nothing, this is a business as usual, you do nothing about climate change, you just ignore it, then the growth in GHG emissions would grow from roughly 600 million tons in 1990, or it was up to just over 700 million tons in 2010, and that would then increase to 1.1 million tons in 2050. So the key thing for this diagram is like I'm showing that even though the economy doubles, or the GDP doubles, that the rate of growth of GHG emissions increases by about 60%. So it increases less rapidly than growth in the economy. But the mix stays remarkably similar. There's no fundamental changes that occur in end uses or in the supply side or in the non-combustion emission areas. But when we now begin to address the question of GHG emissions, we show S1, which is really the diagram that you would get. This is combustion emissions, diagram that you would get if you just ignored climate change. However, climate change, we wanted to look at the impact of climate change. So we had looked at ranges from 30% reduction to 60% reduction, represented by R30 and R60 and so on. So that shows these diagrams from 2011 to 2050. So this was the driver, was what was required to get from the S1 diagram, S1 result down to the R30 and R60 results. So these are wedge diagrams. So I'll just show a couple of results. Obviously, there were hundreds of results in the study, but this shows, for example, 60% reduction. We had difficulty getting to 80% at the time that we did the study because we had special problems with auction for heavy freight transport. But the key things, so what is shown in the upper part of this wedge diagram are the reductions, and in the lower diagram is the result. And the dotted line basically is the GHG emissions profile. So the key takeaways from this diagram are that the first priority is really to decarbonize electricity supply. You see that in that triangle in the bottom, the brown triangle at the bottom, which basically shows that very quickly your electricity system in Canada is the first priority to be decarbonized. Then following that, the most important early sectors for decarbonization are really to decarbonize the what we call the supply system, which is really the whole fossil fuel supply process, which includes refineries and transportation systems and so on, and the transportation sector. The transportation sector is a very important sector to decarbonize quickly. In later studies, we actually show that the transportation sector needs to be takes on higher priority for early decarbonizing. So this is another scenario which is intended to be sort of another extreme, but in fact the results are a little bit different. Not that different, because it still is telling you that the first priority is to decarbonize electricity supply and so on. So I want just to show what happens with end uses. So this is a diagram which shows that in terms of meeting end uses, 2011, the mix today, this is in terms of petajoules of energy, is dominated by hydrocarbons for meeting end uses, which is dominantly oil and gas, which is about 74%. Then electricity about 22%, which is the light blue, and then the biofuels biomass is about 4%. So as you go forward in time to 2030 and 2050, you of course see an increase, but you see an increase in all those, but the ratios, 74% and the 22% and the 4%, stay remarkably constant. So that's really the takeaway, is that if you ignore climate change, then you just see progressive increases in emissions. So this diagram now includes what was in the previous diagram, but now shows the results of 4 scenarios, which represent a range of extremes over a period of time. So the key thing here, first of all, there are three key points, takeaways from this. The first is that when you bring in climate change considerations, then the actual increase in energy end use does not increase. It stays remarkably constant. There's some variations and so on. So this is kind of a counterintuitive result, that even when you are dealing with very extreme scenarios, you wind up getting roughly the same result for the amount of energy that is used. So that's the first message. The second message is that the mix of energy for meeting end users changes really dramatically. So the fossil fuels, which in the do-nothing scenario represented 74%, by the time you get to 2050 and you're meeting the GHG emission constraints, the electricity component will have increased from 22% to about 60%. And the role of fossil fuels will have decreased from its 74% down to around 25%. And the biofuels will also have increased from around 4% to 15%. So those are the major changes. So what we're really looking at, if we're going to meet the emission constraint, is a massive reduction in fossil fuels for meeting end uses, particularly in the transportation, buildings, and industrial sectors, and a huge increase in electricity supply to meet what is essentially a major end-use electrification program. This next cost slide now shows the costs. These are the marginal costs which came out. So the key thing here, there's a few messages. What's important to appreciate here when we talk about marginal costs for mitigating combustion emissions, what this really means is the cost for the last unit of CO2 emissions that have been reduced from the system. So these costs, you know, first of all, they increase over time because all of your most cost-efficient solutions come in early, but then you're putting in the more expensive options as you go forward in time. The second comment is that you're looking at costs in the order of hundreds of dollars per ton, not tens of dollars per ton. And so those are the really important points here. So when we talk about carbon pricing as the mechanism for reducing emissions, these are the values that you would need to be prepared to put in order to get the reductions, assuming that the economy responds perfectly to these kinds of price impositions on the economy. So it's very important to understand that the marginal cost of CO2 emissions is much higher than what people are generally think it is or what they're prepared to really talk about politically. So what were the principal observations of the study? Well, first of all, deep reduction pathways result in major end-use changes. These are really dramatic changes. And when you look at it in terms of electricity supply, for example, we would be looking at electricity capacity increasing from its current 135,000 megawatts to well over 500,000 megawatts when you also include that all your intermittent renewables also need backup capacity. So these are massive changes. In the study that we did, we only got to 70%. We didn't actually get to 80%, but in later studies where we were able to bring in the new technologies for heavy freight transport, then we get up to 80%. But getting beyond 80% is really a challenge. One of the surprising things was that carbon sinks are required well before 2050. There's a sort of a general expectation as we deal with reducing emissions and leave carbon sinks for later. What we showed is that in fact it's critically important to deal with carbon sinks now and figure out exactly how the role of carbon sinks. So the challenge to achieve 80% and higher reductions is pretty huge. We also, in our study, we were looking at plants being able to implement solutions very quickly. So we had very ambitious timelines for when projects could be brought online. and when developers could be changed in end uses such as decarbonizing the housing sector and so on. And the final comment was that it was pretty clear as to where we should start. We should focus on decarbonizing electricity supply. We should move very quickly on the transportation sector and very early on the decarbonizing the fossil fuel sector. But it's clear where we start, but there's a lot of things that are not known, and this is why it's so important to have a very aggressive program of research and development that leads us to implementing solutions in the 2030 to 2050 period that we may recognize today, but are not really at a scale of being ready for incorporation. We also briefly touched on the economic opportunities. It's not just a problem, but it is, there are economic opportunities associated with the whole process of transforming the energy sector and meeting GHG mitigation targets. So Canada has the lowest cost electricity in the G7, so it's possible that as part of the electrification program that we recognize that we're in a favorable global position with regard to the production and export of relatively low cost emissions to electricity for heavy energy intensive products. The cost of electricity in Canada is lower than in the US, so this represents a favorable export market. The forestry sector is an important place to focus on for a sink, developing sink, not only in terms of planting more trees, but also increasing the amount of long life harvested wood products such as lumber, timber, strandboard for building construction, and reducing the amount of steel and concrete for which are emissions intensive construction materials. Also, that there's a lot of innovation going on with regard to reducing the CO2 footprint from petroleum, and that there's lots of innovation capacity in Canada. So that is kind of the results of the study. So I'm now going to go on to the third part, which is to talk about where are we. So this is the first diagram, and I'm sorry that the print is small here, but I'll just explain it very quickly. So since 1990, which is here, we have entered into 4 international agreements. The first was the Rio Earth Summit Accord, which was that we would stabilize emissions by 2000 at 1990 levels. Of course, we missed that by a huge margin. Then we have the Kyoto Accord, which is in 1997 or 1995, or 7, which was to get emissions at 6% below 1990 by 2008, 2012. Of course, that's been missed. The third was the Copenhagen Accord in 2009, which was 17% below 2005 by 2020, which is this year, and of course we will miss that. And then the Paris one, which was 30% below 2005 by 2030. Now, in addition to that, we also have the further commitment of getting to net zero by 2050. So this is not a great track record. So what needs to change? These are just some overview perspectives. This is not intended to be exhaustive, but just for discussion. So what is really required in terms of national leadership is joint national and visionary political leadership. That this should not be a matter of partisan politics. There should not be a position by the various political parties. And I'll come back here to the UK, where Tony Blair, after the Gleneagle Summit in 2005, was able to convince all the parties in the UK that this was a matter of national urgency, and to try to make sure that all of the political parties were aligned on the importance of achieving success with regard to mitigating greenhouse gases. So when the Climate Change Act was passed in Parliament in 2008, it was passed by a majority of more than 99%. So there was no debate between the parties when it went to the final vote. So that was an example of great political leadership. So we should learn from that. We should also learn from other countries. I mean, Sweden and Norway have both been reasonably successful in implementing programs to achieve their respective goals. There is a need for a legislative agreement which incorporates, which lays out exactly the process and the requirements and accountabilities and the institutional capabilities that are required in order to be able to deliver on the commitments. We need a very strong, respected institutional capacity, which is committed. There has to be a committed to comprehensive, integrated, fact-based planning, which is analytically rigorous, so that it looks at the full interaction between all the sectors of the economy and includes climate change as part of that overall process. And that needs to be national cooperation, and there needs to be honest public discourse. When I say honest public discourse, we need to move away from the highly polarized debates that are going on at the present time, which tend to focus not on the whole system, but on components of the system. So this is what's required in terms of national leadership. In terms of key technical opportunities, there are many technical opportunities. We can build around the Canadian advantage with low-cost electrification. We have to look at the changing role of hydrocarbons, which currently represent 87% of Canada's primary energy supply. So the hydrocarbon sector is not going to disappear, but it needs to change in a very fundamental way. It needs to change away from directly meeting end users to really being playing more of a role in terms of intermediary roles. It also needs to look at non-energy uses for the hydrocarbons, and it needs to look at a different product mix after what's coming out of the hydrocarbon sector. We have some great Canadian strengths as examples. The carbon capture and storage. One thing that is not recognized is that Canada is a leader in carbon capture and storage, having built and brought into operation the first electricity generating plant in the world with carbon capture and storage, which is in Saskatchewan. That's the very first in the world at commercial scale. And then that's at the Boundary Dam. And then the similar development with the Quest project in Alberta, which was associated with the Shell plant. So these are both successful carbon capture and storage projects. We need to look at carbon retention, long life harvested wood products. Canada has an amazing amount of carbon reserves in its biomass. In fact, the largest amount of carbon reserves in its biomass of any country in the world, including Brazil, and something that most Canadians will recognize. But we have the opportunity to sequester a lot of carbon, both in the biosphere and in the production of harvested wood products. We're a trusted exporter of goods and services, so we need to look at what are tomorrow's products and their competitiveness in the global market. So that's my presentation. Let's thank you for the 45 minutes. It's over to you, and I'm happy to answer any questions that you may have. So thank you very much for this opportunity again.
Thank you.
My presentation.
Thank you so much, Dr. Sigwell Dawson. So we will take Q&As now. So we have a lot of participants. If anyone would like to ask anything, Professor Sigwell Dawson is available. Please go ahead. If there is no questions, then you can certainly get in touch with Professor Sigwell in the future. I will be posting the recording of the entire webinar on our WISE YouTube channel, and you would be able to access it. But Professor Sigwell, I have a quick question, and this question came to me from a grad student. He was wondering what role can climate finance or green finance can play in order to reduce carbon emissions when it comes to topmost polluting countries in the world. If you would like to answer that particular question by any chance.
That's a very good question. As you know, Mark Carney this is one of the areas that he is very much involved in now that he's left the Bank of England and is returning to Canada. And we also have quite a lot of attention being given by the Canadian Big Six banks on green finance. It really is an incentive to provide favorable funding for green projects that really support some of the early research and development activity and so on. So it's still it's a source of money for moving forward with innovative initiatives. So I think that's the main purpose of it. But certainly in Canada, there's a lot of interest and there's a lot of support by some of the big six banks on that. And there's some work being done by Glenn Hodgson, actually, with the former chief economist of the Conference Board of Canada. He's been looking at the role of green finance in helping to move the climate change agenda forward. So that's not a very informed answer, but perhaps provide some early perspectives.
Mm-hmm. I agree with you, Professor Sigwell-Dawson. If Dr. Sigwell-Dawson, my apologies. And if there is any other question, I would give all the participants a quick moment if they have anything in their mind and if they would like to ask, please go ahead.
Hi, I have a quick question.
Mm-hmm. Go ahead.
So I was just wondering, I saw one of the graphs. I could be wrong, but I saw fossil fuel being used until 2050. And I was just wondering, due to climate change issues that are occurring right now, why is fossil fuel still being used till 2050 when we could bring other alternatives or try to use non-fossil fuel energies and encourage that?
So I didn't hear that question clearly.
Oh, sorry. Okay, sorry, can you hear me?
Yes.
Okay, so I was just wondering, on the graph, one of the graphs, I saw that fossil fuel use will be until 2050. And I was just wondering, with climate change occurring today, why is fossil fuel still in use until 2050 when we could use non-renewable energy or other alternatives that are in place?
So the question is, what would be the role of fossil fuels in 2050?
Yeah.
Okay. No, that's a good question. Really, as it is at the heart of a lot of the debate at this time. So I think there are multiple answers, but I can give you some examples of where the role of fossil fuels could change very significantly. One area that I'm looking at, and I'm doing this with a consulting engineering company to look at the potential for natural gas with carbon capture and storage. The argument here is that when we electrify end uses and we're increasing the amount of electricity by threefold, let's say, assuming that we are taking a very aggressive position with regard to greenhouse gases. What this means is that there's a huge increase in the amount of electricity generation that is required to meet this increased electricity demand. So when you look at the options for that, the role of intermittent renewables, including storage with intermittent renewables, which could be batteries and or pump storage, the maximum amount of energy supply from that option is around 20%. It depends on the composition of the rest of the system, but it's very difficult for it to go much above that because of dispatch limitations. And this is a problem that has occurred. It actually has occurred in Ontario, where even though they have a lot of intermittent renewables, they are not able to actually generate, and they ask owners of intermittent renewable facilities to not generate, but they pay them as if they could generate. But this has also been a problem in both Germany and Denmark. So you then have to look at where does the other 80% of the electricity come from? I mean, wind and solar is very inexpensive, so you should maximize that to the maximum extent possible, but you are hitting a dispatch constraint. So then when you look at the alternatives for supply, it includes hydro, nuclear, and thermal. Those are the three dominant sources. There is also geothermal, but it's very, very small in the overall scheme of things. And so hydro in some jurisdictions like Saskatchewan and Alberta is a very limited resource. You can build transmission lines from Manitoba, British Columbia, but even the availability of hydro is limited. Nuclear has been rejected as an option in those provinces. It may be reopened, but there are huge challenges with nuclear. And so then you're left with thermal. And the option of thermal with carbon capture and storage then begins to surface as a very important option in certain jurisdictions in Canada. So this is one option that we have been studying with Hatch, and have shown that even when you take into account the cost of CO2 that is emitted, because it's not 100% capture efficient. The work that has been done so far shows that we can capture 91% of the emissions. You still have the 9% that's left. So it's not a total solution, but it's very close to a total solution, complete solution. So we believe that this could emerge as a very important option in future electricity supply systems. Now, when you look at the rest of the world, globally, 67% of all electricity that is produced globally is from thermal sources, dominantly coal and natural gas. But in future, any thermal option will need to include carbon capture and storage. So carbon capture and storage becomes a very, very important option in part of the overall solution. But so when you look at carbon capture and storage, it's not only for electricity supply, but it can be for other uses like fertilizer production and cement production and so on. So the whole product mix for the hydrocarbon sector needs to change, but there are also opportunities that people are not thinking about now that almost certainly will emerge as being very significant and potentially very major. So that's kind of a partial. That's an example of how the role of hydrocarbons could change in future. I don't know whether that answered your question.
Thanks.
Hello?
Yep, I think we have a quick question, and then we go to Professor Wu and then to Kian. So one of the participants have posted a question. It says, has there been any attempt to improve the understanding and contribution of non-combustion sources of greenhouse gas emissions?
Also a very good question. People to a large extent have tended to ignore non-combustion emissions mainly because the technology is not well developed for solving emissions from non-combustion sources. So, you know, and some of these are in fact very difficult. For example, in the agricultural sector, most of the emissions are from animals, which is methane releases, and from fertilizer, nitrogen fertilizers. So those are dominant. Now, there are things you can do with nitrogen fertilizers, like better management practices and so on. But a lot of agriculture in Canada requires nitrogen in the soil, so that's a challenge. So we sort of acknowledge that there's probably a limit as to how much you can achieve in the agricultural sector. With regard to industrial processes, again, the options are not well defined, and they're very complicated because you have a large number of different industries in Canada, and each one of them has their respective processes which emit emissions, not just CO2 and methane nitrous oxide, but the petrofluorocarbon and so on. And so you need to come up with very specific solutions for those, which may require process changes in many cases, may require thermal capture and so on. So this is just a huge area that is we really have barely begun to address. With regard to methane releases, this is a very serious problem, and we need to strengthen the regulations with regard to that, because methane has far more serious short-term global warming potential than CO2 and so on. So again, this is an area that requires not only study in terms of knowing where the releases are coming from, but also looking at alternative ways of regulating that to reduce those emissions. So I guess the overall question is that this is a huge area that requires an enormous amount of research and development, and to look at all of the different sources, you know, in a much more detailed way. And one of the things that we brought out in the Trotte work was that if you just focus on GHG emission, combustion emissions, you could very well wind up 30 years from now being that the dominant source of emissions is actually non-combustion emissions. So you can't ignore it, you have to deal with it at the same time.
Perfect. Now we will go to Professor Wu and then to Kian. Professor Wu, please go ahead.
Yeah, so thank you, Oscar, for the talk. So in one of your slides, you recommended for the long life harvested wood as one way to capture the CO2 and decrease the emission of Canada. I was wondering what are your opinions on other type of negative carbon emission technologies, such as direct air capture, and so what do you think about those technologies?
Sorry, which was the one that you mentioned?
Direct air capture.
Oh, direct air capture, okay.
Yes.
Well, I think, you know, direct air capture is interesting, no question, and I've been following the development in that area with great interest. We need to continue supporting the research in that area, because you know, it potentially could be very important. But at the present time, I think there's a lot of skepticism that this could be a cost-competitive solution or cost-competitive option with regard to aligned with ensuring that you're putting your money into the most promising areas. So I know of the work that's being done at in Calgary, University of Calgary, on direct air capture, and continue supporting that and monitoring it. But personally, I have doubts, but that's just from a personal point of view as to whether or not it will ever be a competitive option, mainly because of the amount of energy that is required for the direct air capture process itself. And the argument has been used that you build non-emitting generating facilities as a supply of energy for direct air capture. But in the overall scheme of things, you have to look. Eventually, you're going to have to say, is this a cost competitive option in the context of all the other options that are available? So that's my response on that. But
thank you so much.
Keep all these options open.
Yeah, sounds good.
Thank you, Professor Wu. And now we will go to Kian. Kian, please go ahead. Hello, Kian. Do you have a question?
Is he muted?
He is. Yeah, I think he's muted. Kian, do you have a question? Okay, I guess not at the moment. Is there any other question someone would like to ask? I guess no, not at the moment. No problem. As I mentioned, that the entire recording will be posted on the WISE YouTube channel and on the WISE website as well. And if you have any questions, then you can certainly reach Dr. Sigwell Dawson in the future. So I would like to thank Dr. Sigwell Dawson for his wonderful presentation and all the wonderful insights he has shared with us. Thank you so much, sir. Thank you so much, participants. Thank you so much, audience.
Well, thank you very much for the privilege of being able to participate in your program at the Institute. So very much appreciated, and thank you for the opportunity.
Thank you so much, sir. Okay, have a great day. Bye-bye.
Bye-bye.